Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve a beam element using aster. So now just go to the second slide. This is our truss we have taken. Here we are going to use a beam element, and this is made up of steel with an Young's modulus of 210 gigapascal and Poisson ratio is 0.3. Now we are going to do with linear static analysis, and this truss, this both the point is fixed completely. Here only x translation we are allowing to move. Here we are applying 2500 Newton force, and here we are applying 2000 Newton force. In vertical force, here we are applying horizontal force. This truss having a cross section of rectangular section with 0.1 meter and 0.1 meter. Now we will solve this problem using Salome meca. I'm just opening the Salome meca here. In this case, we are going to generate a command file using efficient software. Then we will be running using ASTK. It's similar to ANSYS APDL command runner. Now we'll see how to solve it here. Now first we just want to define the geometry as well as finite element model. First we'll create the model using Salome meca geometry model. First go to geometry. This one is the geometry model. Now we just go to new entity. First we'll create a points. From that we'll create a lines. So first we'll create a point here, then one more point is in 3 meter. First go to new entity, basic points. X0, Y0, Z0, just apply. It has created one vertex. Then the distance of Y 3 meter. Fit screen. See here, there is one point, there is one more point here. Now we'll create the distance of 4, one more point. X4, Y0, just apply, just go to fit screen again. See, one more point it has created here. And there is one more point which is in the distance of X is 4 meter and Y is 3 meter. Now just simply X is 4 meter and Y is 3 meter. Just apply and close. Now we have created 4 points. From that we just want to create a line. First one is this line. Then we just want to create it. Now just go to new entity, basic line. First choose the vertex 1. Then you choose vertex 3. You can switch off viewing this one, vertex 3. Just apply it. Now again go to the model. From here to here we just want to create. From vertex 3 to vertex 4, just apply. From here to here, just apply. Then now from here to here, now just apply and close. Now you just have a look. We have created the complete truss model. Then we just want to make a single line into one line, because we are going to apply the same cross section to the complete beam. If it is a separate cross section, means we can group it separately. First we just go to new entity, build. There is an option called wire. Just select all the line 1 to 4 by pressing the shift, then just apply and close. Just go to new entity, build, just compound, just apply and close. Now just see, we have created this compound. Now we can save this file. Go to file, save as, pictures, aster. Here I just want to, this one is my folder. I'm just saving it. So after saving it, we just want to create a groups. to apply the boundary condition and elemental property to the beam element. Go to new entity, group, create group. First edge group, select all. This one is the beam. We can give any name. I just, for easy understanding, I'm giving beam. Just apply. Now these both the point, we just want to arrest the degree of freedoms. Go to point construction, select this point and press the control and select the shift and select these 2 points. Just add. Here we just want to fix it. I'm just naming as fix. Just apply. Now select this point F 2500. I have selected this point. Just add it here. This is FY 2500 is the group name. I'm just giving too easy to understand the group. Here there is one more load. We just want to apply it here. This is Fx, force in x direction of 2000. So for easy understanding, I'm just naming like this. This is just a name. So we are not applied any load. We have created the groups. To easy understanding, I'm just naming it like this. So now we can save this. Now we have created the groups. Now we can go for meshing. Go to mesh module. Now we are in the mesh module. Just select this component one, mesh, create mesh. Now you can see it as 3D and 1D are not showing and not enabled because our geometry is just 1D. Just go to wire discretization and local length. I'm just specifying, it's showing 0.5, 0.3. I'm just giving, say OK, just apply and close, right click, just compute. Now you can see it has created 55 edges and 55 nodes, and it is a linear. Just close. If you want to see the nodal nodes how it has created, just go to modification, option, modification, add node. Now see, this is the way it has created the element node. Now just close. Now just check the groups here. Now groups also imported here. Now we can save this file. Now we can export this mesh file. Go to export, MED. I'm just exporting the same folder. Just save it. Now I have exported the MED format. Now we just want to create a setup to run the case. We can create the setup by using aster study GUI also. Or otherwise we can go for efficient wizard. Now in this case I'm going to use this efficient wizard to generate the command file. Just open this efficient wizard. Before that, you just download this efficient and then you just install this OpenJDK Java runtime software. Then only we can open this file using this software. Just open it. Now it is opened. Now we'll set up the case. This is actually a simple linear static analysis. So then go to analysis type. This is not a 3D element. It is a beam element. It's a mechanical beam. You just choose and go to material. We have modeled the material in meter. So I'm just giving a material name of carbon steel with Young's modulus of 210 gigapascal. So for that, just have a look in the material property. It's a 210 gigapascal and point size ratio is 0.3. Because of this linear static analysis, density is not required. Just go to efficient wizard. So 210 e power 9, this 0.3, this is not required. I'm just removing it. Assign to all. Just add it. So it is asking to enter the density. Anyway, now we have defined the material as well as assign the material to all the beam element. Now go to element type, beam, rectangle cross section, assign to the group name which is we have created is beam. So you just copy the name properly and paste it there to avoid the mistake. Then this is actually thickness for hollow section, but ours is a solid section. You just go to y direction is 0.1 and x direction also, z height also 0.1. Then you just make it add Now we have defined the element property and assigned the element property to the model. Now just go to boundary conditions. Here we can go for node group as well as the mesh group. So I'm just going for a node group. Degree boundary condition name I'm just giving fixed. Any name we can give it here, but is assigned to is the very important. Is assigned to the group name which is fixed. So we should not use a small fix because I have used capital F, small I and x. Same way we have to name it. So better is just copy and paste it. Now we just want to arrest all the degree of freedom. We just make it 0. That means we are arresting all the degree of freedom. Now we just want to apply force. We just go to load tab. Here there is an option called force on the node. Any name we can give. Load. First one is assigned to FY underscore 2500 in the y direction minus 2500 because it's in the negative direction, so we have to apply in that way. Just add it. The first we have added. The next one is load y. Any name we can give. Force on the node assigned to, here you can see fx underscore 2000. It is in the positive x. Here you can see negative 2500 Newton force. Here it is a positive x direction in 2000 Newton. So I just naming the same way, positive 2000. Remaining you just keep it the default, just add it. Now I have done both creating load. Just go to output. Here we just want to see all the output reaction forces on the nodes, directional, stress, bending stress, everything. Just add all. Here there is an option called save command file. Just save it. Now just navigate this file to folder where you want to save it. Pictures, code aster, 64th. Here I'm just naming static.com. So here you can see writing of .com file complete. Just say OK. Just close it. Now we can go for the folder. We can open the command file. We can check what we have created. Here you can see this is the mesh file, mesh_1.mad, and this is the command file. This is we have created the command file using efficient software. Now we just want to solve this case using these two files, using CodeAster ASTK. That is available in tools, plugins, CodeAster, run ASTK. Just say OK. Now this is the ASTK version, is similar to the ANSYS APDL we used to run if you have a mesh file and command file, mesh file and script to run the case. Similarly we can run it here also. Now just choose the location where you want, where the file you kept. Pictures, CodeAster, just OK. Now we can save this file also. File, save as, same any name we can give. I just ASTK I'm just giving and it's OK. Now I have saved it. Now we can give the input and output names. First one is we just want to read the, so it's better to understand. I'm just keeping like this. So first we just want to read the command file, then we just want to read the mesh file, MED file. Mail is the format to read the mesh file. Then we just want to take the outputs, whatever the outputs you want. You can message file we wanted, error file we wanted, resu file we wanted, similarly output file. This is the file we require to view the results, RMD format. So everything I have said. So D is nothing but input, this is nothing but output. So I'm just naming it static better // static.com. Same name we have to give. Similarly mesh underscore 1 dot med. Any name we can give. I'm just giving message dot mess dot slash error dot err dot slash resu and dot slash result dot rmad. So this is a message file. If any error comes, we can open this message file. From that we can identify what error is coming. This is a result file. Any result output, we just want to take it from the solver. We can take the result output. This one is the result output in RMD format to view the results in paraviews. Now everything I have set it. Now we can assign the memory, how much memory you want allotted. I just want 100,000 for it. 1 GB I just want allotted. How much time also if you want to allot, you can specify it. 15 minutes is enough to me for this case. And I just go to interactive follow-up, just tick this one and run this capital run. So I'm just saving this file, Control S. Now we can run it. While running, you can see it. This is the interactive follow-up. This file is open. So the case is finished. Just close this window. Now you can check the result file is coming or not. First we have to check the message file. Just open this message file. Check any error comes. Here you can see diagnostic job is come up with the alarm. Read the alarm. So alarm is just simple alarm. It will not affect the results. It is solved with nicely. Now we just go to close. Now you can check the result.rmd file. Here you can see, yes, the file is there. That means it is solved nicely and it is having a memory of 64.5 KB. Here you can see in the bottom. So it is having a result data. Now we can open this result file using a paraview to view the results. Now just go to paraview. It is a wonderful post processor for code aster solver. Just build in and open it. Go to pictures, code aster. Just select this one, just OK. Just apply. Now we got this file. Just go to displacement, X magnitude. Now we can check we can change this color pattern also. Rainbow, blue to red, just apply and close. Here with background we can change it to gradient. From that we can easily view the results. Yeah. Now we are seeing it, but we just want to see how it is getting deforming. This is just a value with a minimum value 6.3 e per minus 6. So now I just go to generate vectors, just apply. Now there is an option called wrap by vector. Just click it here. Just give some scale factor and just apply it. So this is the way it is deforming. Actually we are not applied any roller support here. That's why it's going here. We just want to apply the roller support here. For that we just want to create a groups. Just delete or delete again. So just go to the model again, geometry. Now we just create the group. Same group we have. So we have already created. We can use the same group of FX 2000. This is available here. Now same groups here also. Now we can edit the command file and we can rerun the case. Just go to this one is the command file we have generated. Here you can see this is we can copy it and we can paste it here. This is a fixed I have given. I'm just giving another name called fixed one. Where I just want to fix is here, this group. Just copy and fix it. DX is not 0. This is we just want to allow to move. Remaining are all fixed. Okay. Now I have set this one. This has to be included in the solver, this fixed one. So just copy here and paste it here just name this one. Don't type it because you will get error. While tapping you will make a mistake in capital and small letter difference. So I just, to avoid the error, I just copied the fixed one here. So I've added one more boundary condition I will include it into the solver. Now we can save this command file. You can see it has saved. Now we can rerun the case again. Now we are in the same setup. We can rerun the case. Just run it again. Now it is solved. Now we can check any error comes. You can check the solver. It has taken the added boundary condition also. Now we just go to post processing to view the result. Just go to paraview, right click and open. The result one is result.rmd. Just OK. Just apply. Now you use the generate vector. Just apply again. Now go to displacement vector. Now you see the value is changed. Before we got 6.3. Now the displacement is 3.8. Change this into dx. Now we can go for wrap vector. Just give some scale factor. Just apply. Now see, yeah, here this both the point we have fixed it. We have arrested completely. Here we are applying the load in y direction, and here we are pulling in the x direction. So this is bending like this, and it is getting elongating like this. The static case, to animate this static case, here there is an option called play button. Just click it, create animation. I'm just giving some more frame, 20 frames. Just OK. Now we can animate. See, here we are applying a load in y direction. Here we just pulling it, so it's getting elongating in this direction, and this load also giving some effort. So this is the way it will get deformed. This is actually maximum scale factor we have given. By reducing the scale factor we can see it. So this one is the displacement. Similarly we can see the stress. See per node. This is a normal force in the beam element. So wherever we are getting, we can change this color. Here the red indicates this is getting a maximum stress of 2e per 5. Here we are getting a minus 2.2 e per 5. Here, this one is getting a compressive stress. This one is getting a tensile stress. If you want to see the stress value, just go to view, windows, statistics inspector. Not this one actually. Go to view, windows, selection display inspector. Here you can see the selection display inspector. Select this one to which one you want to see. I want to see the stress. Now just select the node value. That one is the element, actually not this one. Yes. Here it is having a stress of, this is the stress value. This one is a bending stress, sigma n, sigma y, like this we can check. So every data is coming in this way. So this one is the compressive stress. Similarly, where you want to see, you can select the element. Here you can get, see, here you are getting 199,771. This is the value we are getting. Like this we can check the nodal value also. Now we have completed this tutorial. Thank you for watching my videos. Please subscribe my channel for more videos. Thank you.